Thanks for the invitation. Pleasure to be here. So let me first tell you, by now we probably all know this, all listened to Mariusz's talk before, but classical ergonic theory, there are two big theorems that Mariusz was mentioning. So the setting is like this. We have a measure preserving map of a, say, probability space. T is measure preserving. And then we have the following two theorems. So, one is stronger than the other, but the first one is like this. So if we consider this, then this converges to F star in L2 for every F in L2. And that's the Complement Theorem. And then there is the stronger version, which is the pointwise version of this, which is the Birkhoff-Ergonic theorem, which is a pointwise version of the above. So F T N X converges to F star X for every F in L1. And here the convergence is so mu almost every X. And this is Birkhoff-Ergonic. Both very classical from the 30s. But now sometimes you might ask, okay, what happens if you switch the setting a little bit? So for example, T, which is a map of a compact metric space. So for example, we have a continuous map and X is compact metric, then it makes sense to ask what happens for a fixed initial condition, right? So then say you take a function f maybe which is continuous, and then you ask about like sum 1 over n, and you take a point x in x, and then you ask, okay, what can happen if I just sample my f along the orbit of x, but the x is fixed. So notice there is no measure here at this point. And in general, you can't, in this generality, you can't say anything. Essentially, you can't, in this generality, you can't hope for like convergence or something like that. But there is one very useful property, topological property of T, which allows you to study these sums and say what they are. Get the asymptotics, and this is unique ergodicity. So T, so definition, T is uniquely ergodic if the set of, so the set if MT of X is just mu, and this is the set by this is the set of T invariant probability measures. So if my system is uniquely ergodic, so there is just one measure, the set of T invariant measures is always non-empty in this setting. That's a theorem of Krylov and Bogolyubov. So it's always non-empty. If it's as small as it can be, then we can understand this, and it's actually an if and only if. Proposition, or not a difficult observation, is that if T is uniquely ergodic, then, and actually it's an if and only if, but this is maybe what we are going to be interested in this direction, then for every X in X, and for every continuous function F in C of X, we have convergence. We know what the limit is. So unique ergodicity is generally a good property. So if your system has a little bit more structure, then we get this. And this is an if and only function. And the convergence is uniform in X. So one clearly sees that this is a strengthening of both these results. Of course, not all maps are uniquely ergodic. So, for example, if you take a Bernoulli shift, then it's very far from uniquely ergodic. You might have many different statistics depending on your measure. But if there is just one, then you understand what's going on. So that's about, say, the classical ergodic theory. I mean, classical ergodic theorems, where by classical I mean you average over the integers, right? So you, but as we heard in Mariusz's talk, quite often it makes sense, and this is going to be the setting for this talk as well, to talk about non-standard averages, where you are averaging and maybe putting some weights, or you average along a sparser subset of Z of N. So, so non-classical, classical would mean theorems would be, we have a given sequence AN, which is maybe bounded. It's in the integers, maybe AN is bounded. And then say we look for expressions like this, and maybe positive, So here I'm trying to be general, and usually when you're general, there is like something that doesn't work with the definition. So maybe AN is positive, that should be the assumption, and then we put, for example, something like this. And here, just to immediately restrict the generality, I mean, we don't need to, but for a general sequence, it's hard to say anything. So usually you consider some sequences that are important, for example, in number theory. So for example, you can look at some examples would be AN equals 1 if, for example, N is a square and 0 otherwise. You can look at more generally, for example, another would be AN equals 1 if N is the value of some polynomial, where P is an integer variable polynomial, and 0, maybe some more example would be, so example 3 would be, you can take AN, be for example 1 if N is a prime, and 0 otherwise.
0 is a natural number.
Yeah. With what I wrote, I mean, it has.
But in general, they can be not necessarily integer. General setup, you can.
Well,
that's true. Put some weights.
That's true. So I can put complex numbers and then we know that problems here, right? So maybe, well, let's put reals. Then maybe you want them to be positive. Just for, yeah. And of course, complex weights also make sense. And more, so I will write 2 more just to focus. I mean, this is going to be our main focus. Here you can also say if N is a K almost prime, so a product of like almost K primes. Right, so I hope we get the understanding. Here we are going to be studying f t to the n squared essentially, and here these 2 are related very strong. I mean, at least the expressions that we want to study are related to what Mariusz was discussing. So polynomial ergodic averages, but you can also take characteristic functions of prime, or this is like you can take AN to be, for example, the multiplicative function. So like, let me say mu of n, or you can take it to be lambda n. I mean, you can have many choices, but essentially here the 4th case would be you take some value. The function a of n is a multiplicative function. All right, and then of course with this choice of an for each fixed choice, you can ask the same questions. So you can ask, and this is, I'm not going to say much about it, maybe just mention. You can ask what happens, if given a sequence, what happens if in convergence in L2. Then you can ask what happens in convergence almost everywhere, and then you can ask what happens with everywhere convergence. And this is going to be this is what we are going to be mostly focusing on. Now for L2, essentially there is a nice reduction which tells you that if you understand exponential sum weighted by an, then you understand these expressions. I mean, it's an if and only if. So if like I understand expressions, so for L2, if I understand an e to the n beta, for example, it's just saying, I understand irrational or actually any rotations, then you can using spectral theory, you can reduce the question of this to the question of this, and then depending on your sequence, right, for many, for all of these choices, for example, that I put here, hopefully we understand what's going on there, and therefore you have L2 convergence. Now for pointwise convergence, this is what Mariusz was talking about. It's much harder because you need maximal inequalities, circle methods. It's much more depends on your sequence in some sense. In the end, you also reduce it to expressions like this, but you need quantitative bounds and much more complicated. So our goal will be to study these expressions. So I mean, these expressions for every x. So the setting will be. So maybe let me think it here. The setting is that we take. So now the setting is like is a topological dynamical system. We take x in x. We take a continuous function, and we study these averages. And the question is, what can we say about these for sequence for given sequences? And here, how much you can say, it depends very strongly on the sequence you take. So very shortly, we will focus on maybe primes and k almost primes. I will maybe also mention what happens in multiplicative functions. Generally, everywhere results are generally for these sequences are hard to get. So
you're assuming unique ergodicity.
That's a good point. I should say from now on, I always assume unique ergodicity. Yeah, and maybe minimality just to, let's say T is that's a good T is unique. Now I want the regular averages to converge then for every point. Okay, so right, ideal, even though you not always can prove it, the goal would be, I mean, the expectation is that if the mean of your function, so mu is the only invariant measure, mu is the only invariant measure, I mean, uniquely ergodic. And here, the expectation would be that if my function is like a zero mean, then this should be small O of 1. Right? Maybe that's not always the case. It's easy to construct examples where you have limit, but it's not small O of 1. Maybe if you take periodic rotations. So, but generally for nice systems, you expect. I mean, the softer question is you take this expression and you ask if the limit exists. Stronger property would be that the limit exists and is actually equal to 0. Okay, so yeah, and generally it's very hard to get results like this. I want to say, I mean, if you take T to be an irrational rotation, for example, rational rotation, then maybe you can do things And actually, I want to say what we know and what we don't know. There is much more than we don't know than what we know. So let me erase this, and I will maybe split this into three cases, like just discuss three cases of. Maybe let me mention one result that fits nicely here, and this is a result especially related, just to show you that sometimes we can have a nice characterization. This is Bergelson and Richter, which says that if T is uniquely, so I'm always assuming from now on unique ergodicity. Okay, so I'll write it, but if I don't write it, it's still, I mean, T is uniquely ergodic, then 1 over n sum over n lesser or equal to n f T omega. So omega counts the number of prime factors with multiplicities equals 3. So yeah. So that's a nice theorem that you take. I mean, it's slightly different. Maybe you don't put weights, right? It's not here that it's the same expression, but hopefully you still feel that this is like a I mean, you take you sample the orbit along not along integers, but a certain random thing, and right, we get a very clear statement. It's as good as regular averages. All right, so this maybe tells us that the omega behaves. I don't know. That's the way. Well, the very good properties of the level sets of omega, for example. Okay, so now let me move to. I will discuss two cases essentially now. What is known for 4 and what is known for 3. I'll start with 4 because here, especially the last 12 years or so, 10 years, we've seen quite a bit of progress. Here, there is much less progress. So, of course, whenever you have an expression like this, let me maybe just mention what type of questions you're interested in. Right, so, and we are going to discuss these questions in this setting. So question 1, which is a softer question maybe, is just find xt for which, let's call this a star. So this convergence for which star holds. Always assuming unique ergodicity for which star holds, right? And then maybe if you have enough examples, then you can try to do another. Then finding next examples is maybe not that exciting, but what you can do is you can ask, okay, are there any dynamical conditions? Are there any dynamical conditions on T? Okay, think on T, on xt, that implies star. Right, so now you want to be more ambitious. You just don't want to look for examples, but you want to say, like unique ergodicity would be the answer for omega n. Unique ergodicity is also the answer for question 2, and if an is just 1, constant equal to 1. So let me discuss these two questions for 3 and 4. And for 3, we have, like I said, there has been quite for 4, sorry. So let's say an. Let me just discuss it for the Mobius function, but you can talk about other multiplicative functions essentially.
Just to remark that here you have negative weights, and you wanted to keep them positive.
Why do I? Good. Yeah, okay, I'm taking absolute values when I normalize. So, all right. Yeah, now it's, let me try exercise. Yeah, I'm taking absolute values here. So maybe the assumption is that you shouldn't have too many zeros. I mean, you don't want to divide by 0 at the end. But yeah, you're right. That generally weight might be negative. Okay, and then Then as I said, there is many. Actually, usually you start with question. I mean, I would say, right, whenever you have expression like this, you maybe first try to find examples and then look for conditions. But here, let's maybe start with question 2, at least conjecturally. So question 2. So the conjecture by Peter Sarnak from 2010 is that for the Mobius function, the dynamical condition is zero entropy. So let me just write it. If xt is of zero entropy, so sub-exponential orbit growth, then star holds. By star, and now we consider the case of Mobius function. Right. This is the conjecture. I don't know how far from being solved it is, but at least conjecturally we have a very clear property. I mean, a very clear. So this is for question 2, or for problem 2, I should say. But so for question 1, when you see, when maybe you first see this conjecture, you still try to see if there are systems which satisfy this. And I don't want to maybe list the systems or say too much about the systems which satisfy this. There is by now many systems, but I would like to, so for question 1, there is many systems, but I think what is equally important to the systems is what tools they use. What tools are used to deal with question 1 for Mobius, and essentially there are number theoretic tools, and here the main player is behavior of mu on short intervals, and in arithmetic progressions, for example. So this is the breakthrough of Matomaki and Radiviu. You have dynamical tools, and there are essentially 2 dynamic. I mean, I'm just summarizing, trying to summarize. So dynamical tools, there are 2, which is something I'm not going to discuss too much. It's Furstenberg systems. So essentially, you associate a shift system with the function mu, and then you study the properties of this shift system and hope to get some insight into expressions with Mobius. There are nice conjectures there that characterize mu. So you can say in terms of these systems when this Mobius conjecture holds, what does each subsystem have to satisfy. But the one I want to focus more on is because it's our main goal shortly will be to study primes, and for primes you can't build. I mean, primes have zero density, so hard to build a shift system. So this is the DK Plc Criteria. So when it comes from a place I first saw it was Burgen-Sarnak-Ziegler paper on Mobius disjointness for horocyclic flows, and basically what it tells you, you need to understand type 2 sums. So it tells you that you need to understand. So if for any PQ maybe different primes, if we understand expressions like this, if they're complex valued 1/n, the point is here, you fix PQ, that's very important. You fix PQ and then you let n go to infinity. And if you can show, for example, that this is small o of 1, then this implies, this is the criterion, then this implies that well, we have the same for the Mobius function. And this is very useful in ergodic theory, because this now, if you look at this expression and you look at from the point of view of ergodic theory, this talks about joinings of TP and TQ, right? So these, I mean, at this point, if you don't know what joinings are, it's not important. But if you do, the reason the consequence of the fact that we fix P and Q first and let n go to infinity after they are fixed allows us to use ergodic theory. So this is related to joinings of TP and TQ. So invariant measures on the product space, which project onto the only invariant measure. Remember, I'm always assuming unique ergodicity. So this criterion tells you, okay, understand type 2 sums, but quality. So PQ do not depend on that. And part of the many systems in here, for Mobius, the reason why we have many systems in here is because we have, you know, in ergodic theory, we have developed tools to study joinings of TP and TQ. For example, if they are what's called disjoint, so there's just one joining, which is the product measure, then I have it for free. In general, you know, for many systems, we understand joinings, and whenever you understand joinings, you get this. So that's summarizing the story for Mobius. I don't maybe want to go too much into, I would like to shift to primes and almost primes. But this is going to be, I would like, if there's anything so far, I mean, that's going to be important for primes, is this, or almost primes, is this expression here. And actually, the failure. Okay, so now let's move to primes. And this is where actually what I want to talk about. So now, for example, what you want to study is, again, xt is uniquely ergodic, and you want to study some f tpx and normalize by the number of primes, which is log n over n, and you sum of the p less or equal than n. You take mu of f, say mu of f equal to 0, and you would like to know if this exists, or maybe if you're lucky, remember always for every point, maybe this is small o of 1. Okay, so the question is, when can we have this? And something I will discuss also a bit later is that instead of prime, so it will turn out, as you'll see, that primes are extremely hard to get. Like our knowledge about this in dynamics is essentially, I mean, it's not big. I mean, there are very nice examples, mostly algebraic, but not much. I mean, not much beyond that. And like what we studied, and this is where some of the results I will talk about come in, is you take two primes, P1, P2, less or equal than n, you normalize by P2 of n. So these are semi-prime. You take numbers which are products of two different primes, and then you do PP1, P2, X, and you want to see when it's O of 1. We'll see very clearly why this is in some will turn out to be easier. But for now, let's just talk about primes. So essentially, if we ask, again, you can ask about question 1 and question 2 in this setting. And here, I think question 1 is more justified at this point than maybe for Mobius, because, as I said, we don't have many examples. It's essentially, hopefully, I'm going to be able to list the most. So systems for which this holds, these are rotations. This is Vinogradov. And then there are nil systems, or I should say nil translations. This is Green and Tau, and then basically, I mean, there are some symbolic systems, I should say. There are several words here. Bourgain, Green. I mean, it's not a several different symbolic systems that they consider, and maybe Riva. For example, you can show, this is Bourgain's result, that some classes of 3 interval exchange transformations are satisfy PNT. There is no known, just to show you how little we know, there is no known mixing T, right? So T is uniquely ergodic. You can say, okay, say it's mixing for the measure. We don't know if there exists a mixing T. Question: is there a mixing T satisfying PNT? In fact, we don't even know. I think so. PNT. I mean, this. I'm going to call it PNT. We don't even know if there is a mixing T with dense prime orbits. So I'm not asking now about not even about equidistribution, but about just density. So I do TPX and ask about if they are dense in space. In fact, I think the first weakly mixing examples, which are usually much easier to get, I think, is the example of Bourgain, the 3 mixing ITs. And there is a nice paper by Peter Sarnak and Ubis, which gets close to this question, but so like, let me just list this one because we are, so if HT is just 1 T01 on SL2R mod gamma, mod SL2Z, I think in their case, then they know that not periodic. So okay, so TPX, so I should say HPX, H sub P of X enters every set of diameter, and now I don't remember, maybe it's 9/10, I think. I don't remember if it's 4/5 or 9. I don't know if you can see this, but
unfortunately large number. Close to 1.
Yeah, that's what I mean, it's non-trivial, right? That it enters. And of course, you want X non-periodic. If X is periodic, then you have much better. I mean, better and worse in the sense that then you use Vinogradov essentially, or maybe primes in arithmetic progressions. Yeah, but essentially that's it for as far as I can say about the PNT. And the main reason is comes from this thing here. So still, what to do? I mean, we need criterions. The way you go is you look for criteria that are going to satisfy that will imply that the sequence satisfies PNT, so it's equidistributed along primes, and then you check it for the dynamical system. And this, I think, so for this you need steep methods to get primes, and here you need type 2 sums. So to get PNT, you need right? You need what's called type 1 sums. Which I'm going to skip. They are non-trivial, but I think still easier in dynamics. So here you are sampling your system along an arithmetic progression. Not trivial at all, but maybe simpler than type 2 sums. So for type 2 sums, what's the big difference between primes and Mobius? I mean, in terms of applications, is that now the P and Q, you need to, they will depend on N. So basically for type 2 sums, essentially you need P and Q to be as large as, say, N to 1/3, maybe minus epsilon, something like this. Maybe you can do slightly better than this, but definitely you need, you need like a large constant. So immediately you like joinings are out of the picture because right now the P and Q are depending on the N, and type 1 sums are I think, slightly easier to get, although non-trivial. But this is, I think, the biggest obstacle in getting primes.
Otherwise, you might say and point out that in Vinogradov, the type 2 sum is a type 1 sum because of the,
Correct.
and so that's why he never
Right.
singled it out that way.
Absolutely, right? If you have a rotation, if you have a character, so it's multiplicative, then a type 2 sum, right? If you look at this, but you have a character, you can put it into 1, and it's going to be p minus q times n, which is now a type 1 sum. Exactly. But for, if you don't have such nice functions in your space, which is all cases, it's hard to get. There is one. So essentially, I think this is the main obstacle of getting primes. There is another method of getting prime number theorems that we developed with Mariusz Domańczyk and Max Radziwiłł, which is I'm not going to be able to say much about this, but essentially, I probably erased it. Yeah. Okay. So let me give you one proposition that's not difficult to get, but you'll see the flavor of the method that we developed. So if let xt be such that there exists a sequence of primes qn primes, and the distance between tqn and identity is less than, say, 1 over e to power qn. Here I'm not putting the best bounds. Like probably you could do qn to power 1 over n, 1 over a for any a, but just to show you what you can get. So if I'm very rigid, so at times qn,
There's some uniform distance. What's that distance between?
it's supremum over,
4 points.
say, yeah, over all x. So this is, sup over x. You can do slightly weaker than that, but let's just stick with this. Right, so if along a sequence of primes, and actually this is quite important that they are primes, or maybe don't have too many prime factors here, you are close to identity for a long time. So imagine you do qn, 2qn, 3qn, 4qn, up to, you can do like almost like e to power qn repeats. Then TNT holds along a subsequence. So in particular, all orbits are the prime subsequence. So you can find a subsequence in K, and it's very explicit what the subsequence is, right? This is really like more or less like an exercise. It's not very hard. You use the Siegel-Waldfish to get this. But basically you say, okay, let me just maybe write it so you see what is happening. P is less than n. So n, I will tell you what it is in a second. Then you split it into arithmetic progressions mod q, some qn, some f pp x. So p less or equal than n, p congruent to a. Right? And if you choose the n to be like e to square root qn, ppx, t congruent to a behaves just like tax. So in other words, tpx by this rigidity is just very close to tax. And then what happens, you're counting the number of primes that are congruent to p, and this goes out, right? Congruent to a, and you get the regular ergodic sum. So this is going to be like sum over a less than qn. And now you count the primes that are congruent to a, and then you have FEA, up to small errors, I should say, but negligible errors. Right? And then the fact that you have that much rigidity allows you to use Siegel-Waldfish to say that these do not depend on A. You can pull it out, and then you get the regular ergodic sum, which by unique ergodicity is small over 1. So basically, that's the main idea. The fact that Qn was a prime is used to say that you do not omit any residue classes. Normally, you would have to put A and Q are coprime, And this would complicate the ergodic theory part. So now the idea that we had in our work with Max and Marius was to say, okay, if my system T is not close to identity, but can be approximated by polynomials or polynomial phases with a very good precision, then you still have a PNT. Notice we actually proved it. So maybe I'll tell you what we proved, and then I'll just quickly mention semi-primes. So what we proved is that if you take a transformation xy maps to x plus alpha y plus phi x, so this is a class of distal transformation. Phi is a smooth function. These are on two torus. So a transformation of T2 to T2. If you call this T, then PNT holds for T. This is kind of the exercise that prepares you to prove this theorem, in the sense that it turns out that this system is well approximated by polynomial phases. So maybe you don't have X, but TQN is close to something polynomial. And then the problem reduces to understanding polynomials over primes in short intervals. So this was where Maxim did his most of his work in this paper. It was,
If I remember, there were type 3 some.
yeah. So there was an either we had to go below 1/6 plus epsilon in Huxley, or we had to go below 2/3 in Matomaki-Shao, I think. So either polynomial phases or arithmetic progressions in short intervals. And to do any one of these, you have to choose which one you want. I think Max in the end, I don't really, maybe this one. And for this, you need type 3 sum. Okay, so let me just say one last thing, maybe 7 more minutes. I mentioned, hopefully it's still on the board. No, it's not anymore on the board. I mentioned that type 2 sums, to get PNT, you need really a large PNQ to be able to deduce PNT. And now I mentioned semi-primes. So, and let me tell you why. One of the reasons is that okay, so now we do 1/pi2, so the number of products of 2' P1.
1/3 is related to the fact that if you have type 1 sums at square root level of distribution, if you have the type 1 sum at full n to the minus epsilon, level almost, then you would only need a power there. I mean,
probably you're right. Yeah. So
I think it's all in Ivanich.
Friedlander, Ivanich, and Duke, I think. Yeah. So yeah, generally what you do is you do 1/2 minus epsilon here and 1/3 minus epsilon here. But if you can do better here, you can do less here. So if you had, I think this is, by the way, what Green and Tao used for nil systems. They were somehow able to reduce the type 2 sums to really a low thing by controlling.
Yeah, the first one you can go.
But then it doesn't matter how P and Q, how large you have, what in the nil systems, it doesn't matter how large an element you take.
Maybe you're right.
So you can control these sums for whatever level of almost.
Yes, maybe you're right. I was still thinking that they did type 1 with a very good, but maybe you're right that
they have a rate of convergence, so it might be.
Yeah, maybe.
Because they don't just have little one, they have little.
I didn't mention, yeah. That's actually very important. All these type 2 and type 2 sums, you can't hope for 1. Usually you need a log saving. Yeah, you need like
That
1/log cubed n or something like this. Yeah, definitely. Sorry, I forgot
that the type 1 sum square root cancellation is the best you can hope for in kind of horror cycles, say. So that's why the 1/3 becomes so important.
And I think in your paper with Ubis, you did 1/4 here, maybe? You did one?
We missed it, yeah.
Okay, so let me tell you why these are more approachable, and this is our recent work with Mariusz and Max. So now you study products of like E2, almost semi-primes, numbers that are product of two primes. And then we have a criterion. This is me, Mariusz, and Max, to say that if you have, I mean, it's not very difficult, but if you understand type 2 sums, so let me write it, TP and X, F, EQ and X are like less or equal than a constant, say, n over log cubed, and you still need quantitative, but the main point is that now P and Q are less than n to the power epsilon. So P and Q are primes, still not joining, so you need some quantitative bounded. Actually, it's important in our work that we do n2, you can do a little bit something like 1 over log t or something like this. You need less than epsilon, log n, sorry. So if you have this, then you have this, essentially. And then this pairs well with some system, you know, like say you have, there is plenty of systems, and this is what we study, for which you understand joinings, or you understand type 2 sums up to a small level, n to power epsilon, or we even need less.
Here, right, this polynomial, this result, Gn is here?
This is what I wanted to say. Yeah,
okay.
exactly. So if you want, this is what we are working, like we are working with Mario. I mean, this is one of the main applications, it seems. I mean, we started this work like 3 years ago, and maybe we're not so, I mean, we had some systems, but then there is the work of exactly of Lindenstrauss, Mohammadi, and Wang for Horo cycles. So let me just finish by saying this. So there is a recent announcement or paper by Lindenstrauss. Hello, Lindenstrauss.
Presented first. This.
And Wang, Zhen Wang, that says that if HT is, you know, I still have it. So this is the setting. Gamma is an arithmetic lattice. So let me erase this. You take an arithmetic lattice, and then you have type, I mean, they do integrals. So let's do, let me just write what they have. So they have like f htx times f hty. And this is small. So this is like less than constant times t to 1 minus, sorry, 1 minus delta. So you see it resembles that. So take xy. So you have either this or xy is close to a periodic orbit. Of course, you can't hope to have it for any point. Just take x equals y, then you can't hope to have bounds, right? But basically, this is what they say. Like you have saving, polynomial saving, unless your point is kind of a diagonal. Well, it's more than that, but I don't have time to explain it. So basically, they say that you only fail in, you understand when you fail, and then you know, we are working to show that if you take,
That's an effectivization of Ratner.
yeah, so this should be understood as effective Ratner, right? So you have HT cross HT, and you, and essentially they are optimal, right, in what they do, in the sense that you can never hope to have it for all points. But in our case, it turns out that, you know, if you want to study this now, you apply some renormalization because you have TP and TQ, and there you have HT cross HT. So what you need to do is first you go from flow to time one map, and this you can use for example, Venkatesh method. If your flow is mixing and equidistributed, you can go from this to sums, and then you change the sum of P and Q into the sum of T and T, but the point changes, like you use renormalization. This I think is already present. A non-quantitative analysis of this is present in Bourgain-Sarnec. So now the point is, yeah, okay, I think I'll So this is what we are working on, trying to get systems, more systems with PNT. We can do more than the horocycle, but this is, I think, with this result, it's yeah. So thank you.
You have I'm very interested if you can formulate something that's the great generalization of the prime number theorem. So which systems, what's a sufficient condition, say it's uniquely ergonic, for a system that it might have a prime number theorem. So, so the disjointness from Mobius is kind of robust, but the prime number theorem is very, because you can always go to zero density and stuff.
So yeah.
So do you have a natural? So I mean, homogeneous dynamics is probably one.
No, I think one thing to point out is that it seems quite plausible that for every system you can find another system that's isomorphic to it, and in the other one that PNT fails. So it can be just that you need some quantitative. So I think this is something to explore. So you want to. This is a quantitative. I think you need something quantitative on your system. And of course, this is a very strong property as written, but you can weaken these properties to, as I said, to like polynomial, approximating your system by polynomials, and this would give a PNT.
So you lose mixing.
Not necessarily, no. So I was able to show that there is a mixing system with dense prime orbits. I didn't mention this result. So Sarna Kanigowski did like
So conditions like this.
well, but if you approximate it by a polynomial, so I can't imagine that the growth is linear. So then you can approximate your system by a linear phase. And then you can make friends mixing and this approximation. It can be rigid. No, definitely not. Here you fail to be mixing very much, but you can work on that higher. Yeah.
So you said a lot about positive results, but don't we have some counterexamples too for some skew products?
Yeah, so we do. So if you take, I erased the result, but we did x plus alpha y plus phi. If phi is analytic, we show the PNT. If phi is continuous, we show the PNT might fail. In the worst possible sense, so there is a point which has no limiting behavior, not only that we don't know what happens if you do C1, for example.
And just to make sure that I understood this correctly, so by combining your method with this recent result, are you saying we have a semi-prime number theorem for these status?
We wrote a proof for co-compact lattice, co-compact and arithmetic. If it's not co-compact, the thing gets complicated. I can, for example, you need Ziegel-Wallfisch to order of this, and then you encounter Ziegel zeros. This is what we are working on. It's not trivial.
Your result also gives some bounded product of primes that would, like your result.
If you have many primes, you know, I think we can do, I forget what we did there, but not two.
Yeah, but you do density or equidistribution?
I think you can get.
Yeah, whatever you can get. So the whole point about lying almost prime is that you can get by just with type 1 sums, and we.
Okay.
Yeah, we mastered the type 1 sum.
Some bound that would come.
I just want to,
I think.
maybe I can say something here why Radin is so deep. The type 1 sum you can do with harmonic analysis and number theory, and that's modular forms. That's how we do it. It involves spectral theory. It involves a theorem of a much easier theorem of Radin about the speed of equidistribution of horocycles. And you can build in this T to the P. And so the type 1 sums, we have a lot of, we don't have the type 1 sum up to level M, which would allow you then to get by with what you're doing down there very little. But the minute you try to do type 2 sums, which are the joinings, then it's only Ratner that can handle that. Harmonic analysis has never handled Ratner's theorem just with a product of two self-joining. And so we squeezed whatever you could get out of type 1 sum. Yeah, that's correct. But
But you're limited to doing 10 to the 1/2 for type 1 sums.
we got down to n to the half. And we did, yeah, we were able to get to n to the half.
And why are you limited to not being able to get beyond that?
That's the Ramanujan conjecture. The equidistributed, it's like the zero, it's like in Bulgarian graph. You don't have, this has got a serious complexity to it as opposed to a rotation. The actual remainder terms are fluctuating in size square root. So any further cancellation there would mean you have to get cancellation in the signs of the Hecker eigenvalues. So yeah, maybe you can, but it's very much like the square root is what you get from Riemann. But here we know Riemann, basically. We know enough that Riemann's true. So type 1, we're very happy with, even more generally for maximal horospherical. But Ratner, the minute you self-join, harmonic analysis dies.
I didn't know
That's what-
type 1 allowed to get equidistribution of KO, like K,
We did do something with that, I think so.
or it's just, I thought it's just
That's from the argument.
Yeah.
I had a math student,
Yeah, but not with necessarily 2, yeah.
something like that with your argument.
Yeah, I think it's in our favor.
Children weights.
Yeah.
Which is kind of close in spirit to this thing, but I don't remember what the bound gives. I don't remember how many.
Maybe we were making almost primes, a dense set of almost primes with the almost primes
Yeah.
being 100. It's like a polynomial, and you try to make the prime values, and you can. It's Brunn's basically. It's just type 1 sums. Yeah, that's.
I think, yeah.
I need to run. You'll be here next week, right?
Yes.
Yes.
Okay, any other questions? If not, then let's think.